Hello everyone. Today I'll be talking about DeepSurv, which is a deep learning extension of the Cox proportional hazards model for survival analysis. I chose this paper because I thought it was a very interesting example of how classical statistical methods and modern deep learning techniques can be combined together. In many machine learning courses, survival analysis is usually introduced through methods such as Kaplan-Meier estimation and Cox regression. These methods are extremely important and still widely used today. However, in many real-world applications, especially in healthcare and user behavior prediction, the relationships between variables are often too complicated to model using simple linear assumptions. DeepSurv attempts to solve this limitation by replacing the linear risk function in the Cox model with a neural network. What I found particularly interesting is that the paper does not completely abandon the traditional survival analysis framework. Instead, it extends the Cox model while preserving many of its important statistical properties. In this presentation, I'll first briefly review survival analysis and the Cox model. Then, I'll explain the main idea behind DeepSurv, walk through important parts of the paper, discuss the experiments and results, and finally talk about several strengths and limitations of the approach. Survivor analysis focuses on predicting the time until a particular event occurs. Traditionally, survival analysis was mainly used in healthcare to study patient survival times. For example, researchers may want to estimate how long patients survive after a treatment or surgery. However, today survival analysis is also used in many different fields outside healthcare. One important application is customer churn prediction. Instead of simply predicting whether a customer will leave a service, companies often want to predict when the customer is likely to leave. This information is valuable because companies may intervene before the customer actually churns. Another important application is reliability engineering. For example, manufacturers may want to estimate how long a machine or hardware component will continue functioning before failure. Recommendation systems and finance also use survival analysis concepts in some situations. One important feature of survival data is sensory. For example, imagine we are studying customer churn. Some users may still be subscribed at the end of the observation period. In that case, we do not know the exact churn time, but we still know that they survived at least until the final observation date. This is called right censoring. Traditional regression or classification methods usually cannot handle this kind of incomplete information naturally. This is one major reason why survival analysis is useful. One of the most widely used survival analysis methods is the Cox proportional hazards model. The hazard function is represented as a baseline hazard multiplied by an exponential risk term. The hazard function can be interpreted as the instantaneous risk that an event occurs at a certain time. The Cox model became extremely popular because it does not require explicitly specifying the baseline hazard function. As a result, The model is relatively flexible and also interpretable. Researchers often prefer Cox models because they can directly interpret the effects of variables on risk. For example, in healthcare, doctors may want to know whether smoking, blood pressure, or age significantly increases mortality risk. However, the Cox model also has several important limitations. One major issue is the linear assumption. The model assumes a linear relationship between the covariates and the risk function. In many real-world problems, especially in healthcare, relationships between variables are often highly nonlinear and complex. For example, the effect of age may depend on combinations of several medical variables. A linear model may fail to capture these complicated interactions effectively. Another limitation is the proportional hazards assumption, which may not always hold in practice. The assumption means that the relative hazard between individuals remains constant over time. However, in reality, these relationships may change dynamically over time. As machine learning became more popular, researchers naturally began asking whether more flexible models could improve survival prediction performance. So, the natural question becomes, can you replace the linear component of the Cox model with something more flexible? This is where DeepSurv comes in. The main idea behind DeepSurv is actually very intuitive. Instead of using a simple linear function like beta transpose x, DeepSurv replaces it with a neural network. The neural network learns a more flexible, nonlinear representation of the risk function directly from the data. Here we can see the overall architecture of DeepSurv. The input layer contains the covariates of or features such as age, medical measurements, or behavioral variables. These inputs are passed through several hidden layers. The hidden layers allow the model to capture complicated nonlinear interactions between variables. This is one major advantage compared with traditional linear Cox regression. Finally, the network outputs a risk score that is used within the Cox proportional hazards framework. So the key difference is that the linear risk function is replaced by a neural network. Importantly, DeepSurv still preserves the overall survival analysis framework of the Cox model while using deep learning to improve modeling flexibility. What I found particularly interesting is that the paper combines ideas from both statistics and machine learning. The statistical structure comes from survival analysis, while the representation power comes from deep neural networks. One of the most important technical ideas in the paper is the use of the Cox partial likelihood as the training objective. In ordinary regression problems, neural networks are often trained using losses such as mean-squared error. However, survival analysis is fundamentally different because many observations are censored. DeepSurv addresses this problem by optimizing a loss function derived from the Cox partial likelihood. This allows the model to properly handle sensor survival data while still benefiting from deep learning. So the neural network is trained within the survival analysis framework rather than outside of it. The paper evaluates model performance using the concordance index, often called the C index. The concordance index measures how well the model ranks individuals according to risk. A higher concordance index means the model more accurately predicts which individuals are likely to experience the event earlier. This metric is widely used in survival analysis because exact survival time prediction is often difficult. Instead, many survival models focus on correctly ranking relative risk. In the experiments, the authors compared DeepSurv with traditional Cox models and several other survival analysis approaches. The results showed that DeepSurv generally performed better when the relationships between variables were nonlinear and complex. Because neural networks can model nonlinear interactions more effectively, DeepSurv can learn patterns that linear Cox models may miss. The paper also explored personalized treatment recommendation scenarios. This is especially interesting because personalized medicine is becoming increasingly important in healthcare research. The idea is that different patients may respond differently to different treatments. By estimating individualized risk more accurately, DeepSurv may help identify which treatment option is more appropriate for a particular patient. Personally, I think DeepSurv is interesting because it combines statistical survival modeling with the flexibility of deep learning. I also think the approach could be useful in healthcare practices, customer churn prediction, and recommendation systems. For example, companies could use this type of model to identify users who are likely to churn soon and intervene earlier. Hospitals could potentially use these models to estimate patient risk more accurately. At the same time, there are also limitations. Deep learning models are usually less interpretable than classical statistical models. This can be an important issue in healthcare applications because doctors often want transparent explanations for predictions. In addition, neural networks typically require larger datasets and more careful tuning. Training deep learning models can also be computationally expensive. So, although DeepSurv improves flexibility and prediction performance, there is still a trade-off between performance and interpretability. To conclude, DeepSurv is a strong example of how modern machine learning methods can extend classical survival analysis. By replacing the linear risk function with a neural network, the model can capture more complex nonlinear patterns while still handling sensor survival data appropriately. I think this paper is particularly interesting because It demonstrates how deep learning can be combined with traditional statistical modeling rather than completely replacing it. Overall, I think DeepSurv demonstrates an important direction for future survival analysis research. As larger and more complex datasets become available, flexible survival models will likely become even more important. Thank you for listening.